Okay, our next task involves maximal sets. Now let me remind you what a maximal set is. We have our interval from 0 to L plus 1, and we put our points on. Whoops, that didn't work too well. We put our random points on. All right, so let's just do this many points. That's okay. And I'll call this one point 1, 2, 3, 4, 5, 6. Now, if we look at intervals that can fit on this, we could fit an interval here, and that contains just the point 1. The first point is 1. So here's the left point, and the right point, we'll put the right point here. So the next one that we get to is 1 and 2. So this is 1 and 1, because 1 is both the leftmost point and the rightmost point. When we move the interval over a little bit, we can include 1 and 2. So the leftmost point is 1, rightmost point is 2. Move it over a little bit more, 1 and 3, 1 and 4. Looks like we can get all 6 in. 1 and 5, 1 and 6. All right. Now at this point, if we try to move to the left anymore, the next change will remove the 1 and start with a 2, right? Because we're moving, think about sliding this interval to the left. That's the next change that's going to occur in the interval. The 1 is going to go out, and then I'll have 6. Then I'll have 3, 6, 4, 6, 5, 6, and then finally 6, 6. Let's just suppose that point number 7 is somewhere out here. So I don't hit that, so I didn't hit that beforehand. So I completely empty 6 before I get to 7. Then the next one would be 7, 7, right, and so on. So what do you see going on here? We see that for any fixed value of L, any fixed value of the left-hand endpoint, we're getting several values of the right-hand. I shouldn't say left-hand endpoint, I should say the leftmost point. Any value of the leftmost point, I may have several values of the rightmost point. The largest value of the rightmost point corresponding to a particular leftmost point gives me a maximal interval. Well, no, it's not quite maximal. That's maximal for 1. That's a maximal integral that begins with for 1 as the leftmost point. That's the maximal interval that has 1 as its leftmost point. This one here, notice that there's only 1 that has 2 as its leftmost point. So this one here is maximal for 2 as its leftmost point. This one here is maximal for 3 as its leftmost point, and so on. So how do we identify these intervals that are maximal for each leftmost point? Well, I find the rightmost point that is biggest. Now, in my IVEC, these intervals are sorted in exactly this way. They're sorted first by leftmost point, then by rightmost point. So what I want to do to identify these maximal intervals, but they're, as I said, they're not quite maximal. They're maximal for a particular leftmost point. The way I can identify these is go down the list and find those leftmost points that occur last in the list. The last place where 1 occurs on the list, if I look at the rightmost point there, that's going to give me the interval or the set of points which is maximal for that leftmost point. All right, now I was stumbling over my words a little bit and saying that's a maximal interval. That's not true. Why is that not true? Because 2, 6 is not a maximal interval. 2, 6 is smaller than 1, 6. 1, 6 includes 2, 6. So 2, 6 is maximal for 2 as leftmost point, but it's not maximal. So once I get this list of circled numbers, that would be 2, 6, 1, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 6, and then go up to 7, 7, like that. right, so then if I just look at these, now how am I going to identify those that are completely maximal? Well, I look at all of the 6s, and I take the first place where the 6 occurs. I take the first place where the 6 occurs. Okay. So that's going to give me my total. So from these, okay, so I can just say from maximal for left-hand endpoints, you need to select the first pair for each right-hand endpoint. Okay, so it's a two-stage process. First stage, go through your list, find the last left-hand and leftmost point in the list, and take those out. And then from that new list, that new sublist, find the first rightmost point. Okay, two-stage process. There may be an easier way to do it, but this works. I'd be glad to hear if you find an easier way. So this code here describes this process. What we're going to do is we're going to take our IVAC, which contains leftmost point information and rightmost point information, break it apart into leftmost point and rightmost point, and then do these searches that I just mentioned. So, first step. First, I'm going to form this vector LVAC, which takes the integer divide of IVAC by n. Now remember, the way we formed IVAC means that if we do this, we'll recover the leftmost point, the index of the leftmost point. And then RVAC, the same thing. If we take IVAC mod n, that's going to give me the index of the rightmost point. Okay, so there are the leftmost and rightmost points of S lying in each interval. Know that LVAC will be sorted, as I mentioned. And for each individual value of LVAC, RVAC is sorted, just like we saw here. For a given value of LVAC, the RVAC values increase. It's like dictionary sorting. Suppose you have Al and Anil and Azar. If you just look at the first two, and then you have Bob, and then you have I don't know, Bull, something like that. If you look at the first entry, the first entries are sorted in increasing order. The second entries are sorted in increasing order only for each fixed value of first entry. So they call this dictionary order. So that's what we have here. We have the same kind of ordering. First ordering and second ordering. Let me get rid of that because it's just more confusing than anything. Okay. So that's what we got. Let's go back and continue. So the LVAC will be sorted, and for each individual value of LVAC, RVAC is sorted. All right, so now what we want to do is we want to pull out, as I mentioned, we want to pull out these values, the values that correspond to the last occurrence of each particular LVAC index. All right, now how are we going to do that? One way to do that is to notice that if it's the last occurrence of a particular index, it has to change to another value. So it changes from 1 to 2. So that's what I want to do. I want to change this. I want to find all the places where the value changes to a new value on the next index. So that's going to be this step here. I'm going to call this vector MVEC. This is a logical vector, and this logical vector is going to be 1 for those entries that I want to keep, and 0 for the 0 otherwise. So when I create MVEC on this vector here, my MVEC I'm going to have 0, 0, 0, 0, 0, 1 here. And then I'm going to have a 1 here, 1 here, 1 here, because these all satisfy the criterion of being maximal for the leftmost point. So these logical vectors are giving me a way to identify the entries that I want. So I want to define a logical vector MVEC of length m-1 such that MVEC of j equals 0 if LVEC of j is equal to the next one, that means that LVEC of j is not the last one, the last occurrence of that particular index. And then it's m, and then MVEC is equal to MVEC of j equals 1 otherwise. So as I said, you can do this with a loop, but there is a faster way. Note that if MVEC of j equals 1, then RVEC of j, RVEC for that index, is the largest possible rightmost point in a vector that has LVEC of j as the leftmost point. I realize that this is a lot of stuff to get straight in your head, but draw pictures, do examples as I showed, and I hope that you'll be able to see what's going on. So at this point, we have identified those entries for each leftmost point that have the largest rightmost point. All right, so let's go on to the next one. We're going to select those points. So if I take LVEC of MVEC, those are the leftmost points that correspond to these changeovers. And the same with the RVEC of MVEC. So I'm going to call that, I shouldn't call that R2VEC, let me call it RMVEC, sorry. That was my old notation. It should be RMVEC. All right, so in this list, for any leftmost point, LMVEC j, the value of RMVEC j is the largest possible rightmost point for intervals with that leftmost value. Note that each point in S intersect 0 to L should appear exactly once in this list, because we're going to look at each leftmost point is going to have a largest interval for that leftmost point. So you can use this as a check for your code. LMVEC and RMVEC will have the same length, and you can call that UL. All right, now, what we're going to do is select from this already selected vector, select a subvector that has the true maximal intervals. So we're going to define we're going to do a similar process, but this time look at RVEC. Okay, so define a logical vector MVEC of length UL such that MVEC of 0 equals 1, and MVEC of j equals 1, so that shouldn't be LMVEC, that should be RMVEC. Let's change that. That should be RMVEC. All right, so you're looking for the first one where it changes. You're saying RMVEC is different from its previous. So that means that it's changed over. Now I also set MVEC of 0 equals 1 because 0 has no previous index. All right. So again, you can do this. You actually can do this in a similar way that you did this one. You can probably copy your code and modify it. All right. So notice that if MVEC of j equals 1, then RMVEC of j is the largest possible rightmost point in a vector that has LMJ as a leftmost point. Okay. So these are actually the maximal. These identify the maximal intervals. So I'm going to set nmax equal to the number of non-zero entries in MVEC. This is the number of maximal sets. The leftmost and rightmost points for these maximal sets are LMVEC of MVEC and RMVEC of MVEC. All right, so I have identified the maximal intervals, and the number of maximal intervals is going to be nmax. All right, so let's ask another question. Are maximal sets more or less likely than others to appear? In our previous example, we did a histogram for the occurrences of sets, and we can do a histogram also for the occurrence of maximal sets. So to answer this question, we may make a histogram for the number of times maximal intervals are chosen. To do this, you can form this vector, n times LMVEC of MVEC plus RMVEC of MVEC, and this is going to give the values in IVEC corresponding to maximal sets. All right, so what I can do is I can loop through these values and count the number of times that each occur in IVEC, and then you can make a histogram of the results. Okay, and what the idea is to compare this histogram to the previous histogram that we did in the previous part. Okay, piece of cake.